Hello guys, welcome again to another video, and in this video we are going to look about some basic theory in integration, limits and differentiation. So we are going to do this because as I've told you in the previous video that in order to move towards continuous random variables we need to know a bit of integration, differentiation, limits, all of them. So I'm going to start with limits. So limits, obviously as the name suggests, you might have also seen it before, limits are a way to find the limiting value of a function at a certain point. So what I mean by this, when I write lim, it means limit, and under it I have to write the variable and the value it goes to. So this expression right here would mean limit x tends to 2. So theoretically it means this. So in a general way, when x tends to 2, it always means that x not equals to 2. Okay, but it just goes towards 2. So if you can imagine the number line right here and 2 is somewhere around it, let's say this is 1.5 and let's say this is 2.5, then the variable x assumes on these values very close to 2 but never 2 from the left hand side, and it also assumes values from the right hand side very close to 2 but never 2. So the values that this variable assumes goes towards 2 infinitely closer but never actually close enough to be equal, right? In a sense that we can actually evaluate the following thing. So how do we actually evaluate limits? So first we write this, and the question could be something like there could be an expression like this, f of x. Okay, now if this is the limit problem we are trying to evaluate, it will have an answer, limit x tends to 2 f of x. Now the answer could be f of 2. You just put in the value of x here only when f of 2 exists, but in more cases than none f of 2 will not exist, or putting just the value of the limit will not work. A common example would be like this: limit x tends to 2 this. So as you can see, if we were to put the value here, it will give us 4 minus 4 by 2 minus 2, or 0 by 0, which is practically undefined. It doesn't make any sense at all. Okay, so therefore, like, this kind of problems need to be handled in a bit more subtle way. What we do here is this: we try to eliminate the factor that's making these zeros come, right? We try to eliminate the factor that makes the function undefined. So here this is the factor, and if you can see, the numerator can actually be factorized, right? How? Limit x tends to 2, x plus 2 whole into x minus 2 divided by x minus 2. And now if I were to say that I can cancel the x minus 2's off, it wouldn't be illogical to ask that why can we cancel them off, because they're literally zeros, right? Because x tends to 2, but then x minus 2, if I put the value of 2, it becomes like 0 by 0, and you cannot cancel off zeros. That would be doing literally the same thing, but in fact we can. This is because, as I said you in the earlier part of this video, that whenever I say x tends to 2, this always implies that x is not equal to 2, right? This means that inside the limiting expression, when I'm not putting the value, inside the limiting expression we can always cancel off the x minus 2's, because x minus 2 is very close to 2 but never 2, so x minus 2 is never 0 actually, because we still have the limit thing on, right? We have not exactly put the value. At the end we put the value of x into the expression, back into the expression when the function is defined at that point. But before that, whenever we encounter something like the zeros, like this x minus 2 divided by x minus 2, where both the terms actually evaluate to 0 if we put the value, you can cancel them off, because inside the limit they are not exactly 0, they are close to 0 but not 0. So this gives you limit x tends to 2 x plus 2, right? And now, since this is defined at 2, this is not like undefined or infinity or anything like that, we can actually use the value of x to find out this is 2 plus 2, which is 4, which becomes the answer. Okay, so this is a common way to find out limits. And now let us introduce to some of the more basic limits that we shall be encountering. Firstly, a note on this regard: if you have limit x tends to a, where a is a real number, and x to the power n minus a to the power n by x minus a, limits of this form have a general answer, and it is n into a to the power n minus 1. Okay, as you can see in this example, where we had like x tends to 2, x square minus 2 square by x minus 2. Here n was 2, if you can match, and a was 2 as well. So the answer should have been 2 into 2 to the power 2 minus 1, which is 4. So it's a general answer. And why is it true? I'm not going to explain right now, because for that we need the factor theorem, or we can use the derivative, which is the L'Hopital's rule, which we shall learn after we learn a bit of derivatives. Before that, it's really hard to evaluate harder limits without using the derivative. So this is the basic which we need to learn here about this formula, and let's do a few examples about this. So example 1 would be limit x tends to 2, x cube minus 2 cube, obviously, by x minus 2. This is a direct application. And example 2 would be something like this: 27 divided by x square minus 9. Now let us do the problems one by one. Solution to 1. This is a direct application of the formula, so this is just for practice, that you remember what we are doing. So x cube minus 2 cube divided by x minus 2. So you can see the n is 3 here and a is 2 here, so it should be n into a to the power n minus 1, right? This just evaluates to 3 into 2 square, which is basically 12, which is the answer. Now this one is a bit easier, but the next part could be a little bit more tricky, because it's not really the formula you think it is. Because limit x tends to 3, x cube minus 27 divided by x square minus 9, right? So like before, we can also see that here if we put the value of 3, it becomes like 27 minus 27 divided by 9 minus 9. But we cannot let that happen, because that would just give you a 0 by 0, of course. But we do know that this is in a similar form as to have the formula we just learned, because this can be written as x cube minus 3 cube divided by x square minus 3 square, right? Now one thing you need to know is, whenever limits exist, different portions of the function can be evaluated separately in multiplication and division form, and also in addition form. Okay, so what does this formula is missing? If you look at the formula which I have defined here carefully, you see that we have limit x tends to a, x to the power n minus a to the power n divided by x minus a, right? We are missing that portion. So what portion do we need here? If this limit were to work, we would need a divided by x minus 3, wouldn't we? But how do we get that? Well, luckily there's two of those, and obviously you need two 1 by x minus 3's, right? So if you divide up and down by x minus 3, what you get is this. This is called adjustment. So in more cases, we would actually adjust the limits to a known form like this. We just divided up and down by x minus 3, which is obviously within the rules. And then again you can divide by x minus 3, because x tends to 3 implies x is not equals to 3, right? This is very important, because otherwise there would be no justification of dividing by 0, right, if x were equal to 3. Now these are two separate limits, right, and you can see they clearly form in the pattern of the formula we learned, but there are two limits and they are in divide form. But as I said, as long as the individual limits would exist, they can be evaluated separately. So basically, since both of these limits exist, it can be written like this: divided by this. So this would give me like limit x tends to 3 x cube minus 3 cube divided by x minus 3 whole divided by limit x tends to 3 x square minus 3 square divided by x minus 3, right? So this would give me the above portion would be 3 into 3 to the power 3 minus 1, and this one would be n here is 2, so 2 into 3 to the power 2 minus 1, right? So let's evaluate how much that is. This is 3 into 3 square, this is 2 into 3, 3's cancel off, the answer becomes 9 by 2, correct? So this is the answer to our question. So this was a bit tricky, but what I wanted to introduce to you was this concept of adjusting. So we will find limits where we might have to introduce something new in order for it to work, like we just did the 1 by x minus 3 thing here in both the numerator and the denominator. But often more than not, we might have to introduce some things by known formulas we already know, and we have to make them work like that, right? We have to make them in a form we already know. That's what I'm trying to say. This basically is the first formula that I would like to show you, and let's go on to another one. Another formula is limit x tends to 0 ln of 1 plus x divided by x equals to 1. So this is another formula. Here ln means the natural logarithm, and we are saying that as x tends to 0, the limiting value of logarithm of 1 plus x whole divided by x is equals to 1. Now, how to adjust? That's what I'm trying to make sense here. So let's see. How do we do that? If we had the limit like this, limit x tends to 0 ln of 1 plus 2x whole divided by x, how would we evaluate this? Because this exactly doesn't go with our formula, right? But you need to understand clearly what it means here. It means that when the variable goes to 0, if you have logarithm of 1 plus that variable which goes to 0 divided by the same variable which goes to 0, this particular expression amounts to 1. Okay, so it really means here that limit x tends to 0, if you have a 2 here and you just write it like this, this expression in the limiting value should go to 0 or should go to 1. Why is that? Because see, if x tends to 0, you can treat this as an equation here, so 2x will also go to 0. Okay, this is entirely true because x keeps on decreasing and goes to 0, so obviously 2x will also keep on decreasing and go to 0, maybe at a slower rate, but yes, it will go on, right? So this means that we can write this limit as 2 into limit. Even if you want, you can just substitute for 2x as y and then write y tends to 0, or you can just simply write x tends to 0 or even 2x tends to 0, which you should not write once you get enough practice, but for now it's okay. It will give you 2 into 1, which is 2, right? So I hope the idea is clear that how to actually do these adjustments like we did here and like we are doing here. Let's go to another one. Number 3. We can write another formula here, limit x tends to 0, e to the power x minus 1 by x is equals to 1. Well, this is one of the same things. This is another formula, and obviously if you had something like limit x tends to 0, e to the power 3x minus 1 by 2x, let's say, and if we were to evaluate this, obviously we need to get it to this form. Okay, so the power of e and the denominator must be same, and we have the minus 1 as well, so this should be 1 if given a proper adjustment. So firstly, this 1 by 2 here is the constant. We can take it out and write it as limit x tends to 0, e to the power 3x minus 1 by x, and then we can have a 3 here, so that we do a proper adjustment by making the denominator equal to 3x, and this shall give you 3 by 2, because this portion is just 1, right? Right. So I hope you get the idea. Now it's time to prove two of these things. So proof 1, we are trying to prove that limit x tends to 0, ln of 1 plus x by x is equal to 1. Okay, see, this is not a very easy proof, but we can walk our way through it. I'll just show you how. Well, first of all, x tends to 0, so this obviously means that we have that mod x less than 1, since x tends to 0, so x is in the close neighborhood of 0, right? So it's like an epsilon distance, which is very small. We can consider as small as we want to be, and it's in that distance in between 0. So basically x lies in an interval like this, where minus epsilon to plus epsilon, and epsilon is sufficiently small. Right? So with this expression in mind, what we can do is we are trying to find a series representation for logarithm of 1 plus x, natural logarithm in fact. How do we do that? Not yet, but let us try to use the theory we have used earlier, which is the Taylor series, right? But in this case we need to find it near 0, so we can use the Maclaurin series directly. We remember that Maclaurin series for fx is given by f of x is equals to summation n equals to 0 to infinity nth derivative of f at the point 0 divided by n factorial into x to the power n, right? And here we have mod x less than 1, since we are trying to find it for logarithm of 1 plus x, which is only defined for minus 1 less than x less than 1. Okay, so the only term we need to find is the nth derivative at the point 0. So let us begin and try to see what happens. So firstly, f of 0 should be ln of 1 plus 0, which is ln of 1, which is 0. So the first term is 0, like the 0th term is 0. Okay, f dashed x in fact would be 1 by 1 plus x, and this would mean f dashed 0 should be 1, right? F double dashed x would be minus 1 by 1 plus x whole squared. So f double dashed 0 should be minus 1. Again, f triple dashed x should be 2 by 1 plus x whole cube, and this would mean that f 30 is 2. right? So this is going to give us a pattern very soon if we just continue it for like 3 to 4 terms, because I do not really want to indulge you with the nth derivative formula directly, which we can calculate directly from here, but let's save that for the derivative portion. So f4 of x again would be minus 6 by 1 plus x whole to the power 4, or in other words this is just minus 3 factorial by 1 plus x whole to the power 4. So this was give us f40 equals to minus 3 factorial. Let us do two more terms. f5x would then be the differentiation of this, which would give you another minus, it will make it a plus, and it will be 4 factorial by 1 by x to the power 5, which would give me f5 of 0 equals to 4 factorial. And similarly f6 of x should be minus 5 factorial, judging by it. It should be minus 5 factorial by 1 plus x whole to the power 6, and this should be equals to minus 5 factorial, right? So as you can see, for the even order of derivative, we have a negative factorial, one less than it, and for the odd we have the positive factorial but one less than the derivative. So we can write that ln of 1 plus x, by the Maclaurin series definition, it should be f0 plus x into f dash 0 plus x square by 2 factorial into f20 plus x cube by 3 factorial into f30, and so on, right? Now once we start putting in the values, we see that f0 is 0 and f dash 0 is just 1. For the even one it's negative, if you remember, so it's not plus, it's like minus x square by 2 plus x cube by 3 factorial into 2 factorial minus x to the power 4 by 4 factorial into 3 factorial, and so on. Remembering that 3 factorial is just 3 into 2 factorial, so the 2 factorial will cut off and 3 will remain. Similarly here 3 factorial by 4 factorial will give you a 1 by 4. Continuing in this way, we get the series as x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus x to the power 5 by 5, and so on. So this basically right here is the Taylor series expansion for log of 1 plus x at the point x equals to 0. Now we want to see that in the limiting case, we were trying to prove that limit x tends to 0, ln of 1 plus x by x, right? Now let us write it under, because the series could be a long shot, so we can use the series definition here, and we can write it as 1 by x into x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4, and so on. Now since we know that x tends to 0 means x is not equal to 0, we can divide by x and we can find that the answer is 1 minus x by 2 plus x square by 3 minus x cube by 4, and so on, right? Now as I know that we can always put the value of the limit whenever the function is defined, here we just have a bunch of plus and minuses, obviously infinitely many of them, but we can write this as 1 minus limit x tends to 0, and then x by 2 minus x square by 3, and so on, okay? But all of these terms will be 0, because when you put in x equals to 0, it doesn't matter how many of them are infinitely many zeros add up to zeros only, so the answer would be just 1 minus 0, or which is 1, and thus we have proved our limit, right? A similar argument can be made for the next one, where we are trying to prove this. where we are trying to prove limit x tends to 0 e to the power x minus 1 by x equals to 1. So starting with e to the power x equals to 1 plus x square by 2 factorial plus x cube by 3 factorial and all the way, we can see that if we just take the 1 on the left hand side and divide by x, what we get is this: 1 plus x by 2 factorial plus x square by 3 factorial plus so on. Now if you apply limit to both sides, what you get is this: you get limit x tends to 0 e to the power x minus 1 by x equals to 1, since it's a constant, plus limit x tends to 0 x by 2 factorial plus x square by 3 factorial and so on. But then again, all of these terms are 0, so the answer should be 1 plus 0, which is 1. Right? I have used this definition because I have already showed you how to get the Taylor series for e to the power x in the previous videos. So I just used the result directly. If you really want to revisit, you can just have a look at the previous videos to see how this was derived. I have done it in every step possible. Now this gives the proof for two of our formulas which we learned, and for the first formula as well, we can actually give a outline of the proof of limit x tends to a x to the power n minus a to the power n by x minus a is equals to n into a to the power n minus 1. So this proof is generally given by factor theorem. So let me state the factor theorem here. It's an important result, so if you want, you can note it down. The factor theorem says that x to the power n minus a to the power n is equals to x minus a into x to the power n minus 1 into a plus x to the power n minus 2 into a squared and all the way up to I do not think this was there, yeah, x into a, and at the last term would be a to the power n minus 1. Yeah, this is the factor theorem. So it factors like expressions of the form x to the power n minus a to the power n. So if we were to use this factor theorem, we could easily see that limit x tends to a x to the power n minus a to the power n divided by x minus a would be equal to limit x tends to a x minus a into x to the power n minus 1 plus x to the power n minus 2 into a and all the way up to a to the power n minus 1 divided by x minus a, right? Now since I have already told you x tends to a means x doesn't equal to a, so we can carefully cross this off and we are left with limit x tends to a x to the power n minus 1 plus x to the power n minus 2 into a plus x to the power n minus 3 into a squared and all the way up to a to the power n minus 1. Now putting the value of x, because now this expression is completely defined and it's a polynomial, we see that it is equal to a to the power n minus 1 plus a to the power n minus 2 into a plus a to the power n minus 3 into a squared and all the way up to a to the power n minus 1. Simplifying, we would get a to the power n minus 1 plus a to the power n minus 1 plus a to the power n minus 1, and all of the terms would be a to the power n minus 1. And how many of them are there? There are n of them, because see, here the power starts from a to the power 0, here the power ends at a to the power n minus 1, so from 0 to n minus 1 inclusive there are n terms, right? So it becomes n into a to the power n minus 1, which is the answer, right? So I've given you proof of all the three theorems that I have used here, because this would be a good foundation to what we are trying to do. So this completes the lecture for this video. In the next one, we are trying to do something with the trigonometrical functions, and we'll try to evaluate some of the limits there. So thank you for watching, and also do not forget to check the link in the description for Breatter Maths, where the lecture videos of this particular video and theory is given. Thank you.